pleasure to be here. I'd like to talk about the equivalence of Hegardt floor homology and embedded contact homology through open book decompositions. And this is joint work with Vincent Collant and Paolo Gaggini, both who happen to be in NOM. Okay, so I'll just start with the main result, which is pretty straightforward, right? So suppose you have a closed-oriented three-manifold, then two homology groups are the same. The one on the left-hand side is Hegardt floor homology. Strictly speaking, this is the HF hat group of M with the orientation reversed. That's isomorphic to the hat group of ECH hat group of M. And, well, Hegardt floor homology, as you all know, probably, it was defined by Ojrat-Sabo. And ECH, which is slightly less known, is due to Michael Hutchings. And today we work over Z-mod 2 coefficients, largely because I really don't know how to orient anything. Okay, so both Hegardt floor homology and ECH are topological invariants of the three-manifold. The funny thing is that, as with sort of most floor theories, the a priori definition actually depends on various choices, and one of them for Hegardt floor homology is the choice of a Hegardt diagram with them. And for ECH, you have a dependence on the choice of a contact form, alpha on n. So I probably won't actually really define any of these things, but I'll give you a sort of definition for both of them eventually. Okay, so the grand scheme of things is sort of something like this. There are at least three floor homology theories. Okay, so the reason I say at least three is that there are actually certain other things which we don't know how to place at this moment. The first one is Seiberg-Witten floor homology. This one is actually, I guess, maybe, I don't really know where it's maybe originally from Witten, and was developed by Kronheimer and Morfka. ECH is over here, and HF is here. And I guess the first breakthrough in this business was isomorphism of upper two, Seiberg-Witten floor homology in ECH due to taus. And our contribution is this one. And there's an alternate proof, the same result due to Gutmann, Lee, and taus. So it's actually this isomorphism. Strictly speaking, the isomorphism, the arrow probably should be more like halfway like that. So I don't know if you can see the dot. It's something like that, where the halfway is some sort of variant of embedded contact homology. So they go through a certain variant of ECH. It's real. The proof is quite impressive. Anyway, so the top isomorphism is due to taus, and it's proof using the circle of ideas involved in this proof of the Weinstein conjecture in dimension 2. So anyways, that's somehow the framework. Are there any questions so far? Besides actually defining anything. Okay, so let's start with contact structure. So the setting is that you have a closed oriented three-manifold M, and a contact form alpha is a one form which satisfies alpha wedge d alpha is basically some positive function times M, and the corresponding contact structure is the two-plane field. It's usually known as C, and it's the kernel of alpha. So for today, I guess you just think of the contact structure as some sort of physical field where each point you're just assigning a two-dimensional plane, which is sort of wobbling around. You don't really need to know too much about the integrability. And to any contact form alpha, you can assign this wave vector field. So somehow it's friend, R sub alpha, which is defined as follows. If you take d alpha first, and then you take the interior, if you take the interior product with R, then you get 0. And then you have some sort of normalization condition that alpha of R has to equal to 1. And if in some sense, if this wasn't so, somehow this definition perhaps isn't really that illuminating. So another way of thinking about a wave vector field is that it's a contact vector field which is everywhere transverse to the contact structure. So your contact structure is somehow a two-plane field, and then your wave is transverse to it. And if you flow in the direction of the wave vector field, you preserve the contact structure. That's basically what it says. And strangely enough, that's sort of equivalent to this contact vector field. And our framework is that of open book decomposition. So what's an open book decomposition? Let's start with a compact-oriented surface, S, with boundary. For most part, I'm going to assume that boundary of S is connected, although that's strictly speaking not really necessary. And you take H to be a diffeomorphism of the surface, which restricts to the identity on the boundary of the surface. So H on the boundary of S is the identity. Then an open book decomposition, S comma H, for the three-manifold M, is some sort of identification. M is, M to be, you take S cross 0, 1 first, and you do some sort of identification, some sort of equivalence. So just sort of imagine, I should have brought this problem. So does anyone have a spiral notebook by any chance? Oh, okay. So this might actually sort of fall out. But suppose this is spiral notebook, and you take S cross 0, 1, which means you sort of have a stack of papers like this, and each of these things is called a page. Okay. And what you'd like to do is do some sort of identification, like this one, and the top row says you take X comma 1, and you identify with X, H of X comma 0. So basically you take the top page, and then you somehow identify sort of with the bottom page like that, with using some sort of monotony. And the second one, sort of, if you write it out like this, is a little bit harder to decipher. X comma t is the same as X comma t prime for all X on the boundary and any 2 points on 0, 1. So basically what this is saying is that you have this sort of spiral notebook, and then you have sort of these spirals. And imagine the spirals are actually not doing this, but actually they're closing up like this. And you basically squash each of these binders or spirals to a point. So that's somehow the squashing the sort of the boundary to a point business. And well, so you just sort of imagine an open book decomposition or something where you have some sort of, you sort of imagine this is sort of sweeping out something like this, and then you have the binding or the spiral part, which is called the binding. Is that good? So that's really an open book decomposition. Well, the monodrome is actually pretty straightforward, but don't mind the fact that okay, now, it's not quite done yet. Right? Okay, an open book decomposition. So we have an open book, and now we have to talk about contact structures on an open book. Okay. And an open book decomposition is said to be adapted to a contact structure if there's some contact form alpha for C such that the rate vector field is transverse to the interiors of the pages, and then the binding is a closed orbit of the rate vector field. So what does this mean? So, well, it's sort of pretty clear what's going on in the interior. So you have your rate vector field that has to be transverse to the pages, or the interiors of the pages, and how could it possibly be tangent to the binding? So it has to do something funny as it goes towards the binding. And what actually happens is that as you're going towards the binding, it actually rotates in this particular fashion, and it becomes tangent. It sort of does this. And so as the binding is actually also an orbit, it's a closed orbit of the rate vector field. So is that good? So the transverse, and as you're going towards the binding, you're doing this. Okay, so I think I'm done. Thank you very much. So the starting point of this work is this work of Thurston, Lincoln, Kemper, Lorisu, Giroux, which says that there's a one-to-one correspondence between contact structures up to isomorphism and open book decompositions up to positive stabilization. So I actually won't tell you what positive stabilization is, because it's not really, well, at least during the talk it won't be important. Okay, so in fact, we actually don't even need the full force of Giroux's theorem for today. We just need to know this theorem of Thurston-Lincoln-Kemper, which tells you that given an open book, given any three-manifold, okay, so that wasn't Thurston-Lincoln-Kemper. Given any three-manifold, it's a classical theorem that there is an open book for it. And they constructed a contact structure which is somehow adapted to this open book. Okay, so let me quickly give you a sort of a false definition of embedded contact homology, but it's sort of, it'll do for today. So ECH due to Hutchings is a variant of symplectic field theory, which is due to Eliasberg given to Hofer, and let alpha be a contact form with non-degenerate vector field, which basically just means you have, I'm not sure what I can say about this. It's some sort of technical condition on sort of basically the orbits being sort of isolated. And if you look at the first return map of each orbit, then you don't have one as an, if you look at the derivative of the first return map, then you don't have one as an eigenvalue. So you basically don't have something sort of going around and basically coming back to the same spot. Okay, and the generators of the ECH chain complex are orbit sets, namely finite multi-sets, gamma consisting of pairs of things. This is a finite collection where gamma I is an embedded orbit of the rate vector field, and then mi is some positive integer. So it's a little bit hard to sort of think about it, but it's probably better to think in terms of like TQFT. We have a bunch of orbits that are sort of here, and then you sort of activate certain ground states by sort of giving it certain integer values. And so we only activate a finite number, and these gamma i's are simple orbits. So we can have orbits which wind around many times. But in this kind of count, what you're doing, you take an orbit which goes around once, right, and sort of doesn't sort of go around. It just goes around once, and you just assign multiplicities to those. So in some sense, you're not distinguishing between sort of sums of orbits which sort of go around 5 times. They have one orbit which goes around 5 times, and another one that goes around once, versus 6 copies of something that just goes around once. You're really not distinguishing between sort of, 2 orbits with different multiplicities which add up to like 6 orbits which add up to the same thing, homological. Okay, and so we use multiplicative notation that looks like that. We'll just write gamma to be the product of gamma I to the mi. And to define the differentials, we consider the symplectization r cross m with some sort of symplectic form, d of e to the s times alpha, where s is the r direction. And so maybe I should draw some figures. So you have so basically the schematic picture is this direction is r, and this sort of flat direction is m. And what you do is you take an almost complex structure J on R cross M such that J takes the ds direction, this is the s direction. It takes the s direction to the wave direction, C to itself, and there's some sort of, I'm not sure what it's called, some sort of calibrating condition. And maybe at this point, the first thing to notice is the following. So if you have a periodic orbit, right, of the wave vector field, and then you cross it with r. So suppose you have a periodic orbit of the wave vector field that looks like this, and you cross it with r. Then this thing that's usually called a trivial cylinder, this trivial cylinder is actually holomorphic. And that's because at every point you're taking the s direction and you're switching it to the wave direction. Right? So that's why so all those trivial cylinders are holomorphic. That's somehow the important point, somehow the important starting point of this business. And what you do in practice, you take some collection of orbits. So you take some collection of orbits like this, and you assign certain multiplicities. And you just count holomorphic curves which asymptotically go to these orbits that you prescribe at the positive end and go to sort of the prescribed orbits at the negative end, such that the total multiplicity at the positive end is the mi's that you're prescribing, and at the negative end you also have mi prime which you prescribe. And somehow I'm seriously lying, but the thing is, you're counting the differential. If you want to take the differential of gamma, some orbit set, and you want to count the coefficient of the differential in front of gamma prime, then it counts isolated embedded J-homomorphic curves sort of in R cross N, which are asymptotic to cylinders over these periodic ends with this sort of multiplicity condition. And somehow the secret sauce is somehow things that make these things embedded. I won't go too much into it. Now, the proof of, so you can define a potential differential, and you ask yourself, well, is d squared equal to 0? Okay. And well, d squared 0 is basically a paper of Hutchings Taus. It's about 200 pages long. It's actually quite intricate. So the d squared equals 0 is sort of 200-page paper. Now, there's sort of other things you have to sort of worry about. ECH was defined using alpha, the one form, and then the complex structure J, almost complex structure J, and you sort of wonder whether it's actually independent of these choices. And it sort of turns out that at this point in time, I don't know, Michael might have a breakthrough at this moment, but the only current known proof of the fact that ECH is a topological invariant and is independent of various choices is through Taus's theorem, Taus's isomorphism theorem with Seiberg-Witten and Floor homology. So, strangely enough, there's currently no direct proof of the fact that ECH is a topological invariant. That is not to say that there are actually ways in which there are plans, there's sort of clear ways in which you can try to attack this problem, but somehow you run into sort of problems of multiply covered homomorphic curves and exactly how to count them and so on. So the problem is really technical rather than sort of not having a sort of a vision to do it. Okay, so now let's start with a wave vector field which is adapted to the open book S comma X. I'm sorry, S comma H. And what we'd like to do is remove the binding from this picture. So recall the binding gamma naught is a closed orbit of the wave vector field. And what we'd like to do is basically get rid of the binding and express ECH in terms of just the data on the suspension end. Right? So where the suspension is just S cross 01, we're just identifying the top page with the bottom page without squashing things to obtain the binding. So you basically excavated a neighborhood, in which case it's a genuine fibration instead of sort of an almost fibration, which has some sort of singular sense. Okay. Now, H, since H is the identity, the boundary of N is foliated by an S1 family of closed orbits. So you have sort of remember the spiral notebook, you had some sort of force on the boundary, right? And then so if you just took S cross 01 and did this identification, then you have a bunch of closed orbits on the boundary, and sort of in fact an S1 family of them. And what you'd like to do is do some sort of Morse spot theory, which means you sort of you pick one orbit in this S1 family, call it E, or pick another one, call it H, and just sort of mentally imagine you've actually done some sort of perturbation, so it looks like a Morse spot situation. So that it looks like a Morse gradient. Okay. Now, so this portion might actually be slightly technical for those of you who are not so used to this, but ECH sub I, let this be the ECH chain complex on N, consisting of orbit sets which intersect a page exactly I times. Okay? So if you have a page, you can have things which intersect as many times as you'd like, but let's suppose you're just collecting things which intersect exactly I times. Okay, then the claim is that you can actually do some sort of algebra and write ECH hat of M. This is sort of the ECH group on the closed three-manifold M. And basically write it in terms of some stuff you collect from ECH of N, which was just a suspension. And how do we do this? you consider the map induced by the inclusions, you take ECH sub I into ECH sub I plus 1 by sending some orbits at gamma and then sending it to E times gamma, where E is the elliptic orbit, okay, in the Morse spot family. And the funny thing is that we're actually sort of, right, effectively when you're doing this business, you are viewing E as the unit. Right? If you're basically, otherwise, if this wasn't really the unit, what you're doing when you're doing this inclusion is just some sort of completely unnatural thing. For this to be natural, this inclusion had better be some sort of reasonable thing. And in fact, you can really think of E as the unit. And as a sort of side remark, in embedded contact homology, so in all these floor theories, to each contact structure, you can assign some sort of generator in these floor homology groups. And in embedded contact homology, the contact invariant for M is given by the empty set. So M comma kernel of alpha is given by the empty set and is usually written multiplicatively as a unit. So in some sense, this is really like, you can sort of think of this as the contact invariant and so on is basically like the vacuum or the ground state. So roughly, how do you eliminate the binding? So you have some sort of binding that's sort of hanging around this. The first thing is that all these things don't depend on the precise contact form that's involved. So it's actually not so hard to change the contact form so that orbits that are sort of, you have the binding, and then you have orbits that are sort of going around the binding. Somehow it's friends, right? It's friends, you can make sure that the friends actually rotate an enormous number of times. You can sort of change the contact structure or contact form so that it sort of winds an enormous number of times. And then it turns out that the index, there's certain indices that are involved, then the index of the binding actually gets sent off to infinity and sort of no longer counts. There's sort of, well, if you want to do this rigorously, I don't really know how to do this particular problem completely rigorously as I sort of described, but roughly speaking, you can sort of you can send the binding off to infinity by spiraling. So roughly the picture is like this. You have an orbit, and you have its friends, that are fellow travelers, like these. And you just make sure that the fellow travelers actually approach the meridian slope as you sort of in the limit. So it's somehow sloped like this, but then you sort of change it so it's actually basically like the meridian slope. And when you do this, the binding will have very large index, and that can be sent away. And in the limit, basically what you have is this S1 family of ray orbits. So in the limit, you'll have an S1 family of ray orbits. So we're sort of successful. Now, the second thing you need to do is, well, this is not the only thing that happens, but what about Follenfit curves, or let's say projections, what about Follenfit curves which pass through this region? So by this I mean you have a Follenfit curve is in four dimensions, but then you can, one direction is R, so you can somehow project down to the 3 manifold, right? And you sort of imagine how it passes through this region, and well, it could actually, it's entirely possible that you had a Follenfit curve that looked like this, and it sort of intersected the binding in that spot, a priori. And then, well, if you get rid of the binding, then where does it go? Right? Somehow you think it might just disappear. Well, am I making sense? So you initially had a curve, some sort of surface, which passed through the binding, right, and sort of cut through this motion. And now, when we're working with N, just the suspension, then, well, you don't have the curve anymore. You don't have this portion. And it sort of turns out that the thing that comes and saves you is that you actually now have these S1 families of orbits. So instead of Follenfit curves which end on, which cut through something, you're now counting Follenfit curves which actually end on one of these S1 families of orbits.
So are you Are you using the fact that ECH is independent of alpha in this?
Yes.
Case? Yes.
Yes. So this is actually some tricky business. In fact, we actually use some results which are still yet still not released by Michael and House. Okay, so that's roughly the point. Okay, so what's the upshot? So what do I gain by removing the binding? So what you gain by eliminating the binding is that you actually now have a genuine symplectic / holomorphic fibration R cross M over R cross S1. So previously, when you have an open book, there's sort of no real sort of fibration, well, not quite a fibration, there's some sort of singularity. Right? We've actually now removed the singularity, and it's actually a genuine fibration, and the fiber is S. So let me just draw you the base of the vibration. You don't have to turn it off. We just have the base of the vibration, and what's happening now is that we're counting holomorphic multi-sections of this vibration. And so holomorphic multi-section just means if you, it's a section. It might have some branch points, but then it's basically a section everywhere, except for certain places when you sort of project down to the base, you might have some sort of branch points. Is this sort of okay or not? Any questions? Yeah, so usually in floor theory, you count sections of things. You sort of have a base, and you have some sort of fibers, and you want to find like things that go through the section, like the fiber once. This time you actually want to count sort of holomorphic curves which intersect the fiber, let's say I times. Right? You sort of intersect each fiber I times, and sort of if you project out to the base, you're going to get a degree I branch surface. Okay, so that's ECH. Okay. Now, Hegard floor homology. And this may actually not look anything like the Hegard floor homology literature. If you're not an aficionado, this probably does not look anything like the Hegard floor homology you're used to, but bear with me. So this interpretation is due to, I guess, Yasha never wrote this up, but Robert Lipschitz in sort of 150-page paper worked this all out. So suppose you start with a Hegard surface of M. In other words, sigma splits M into two handle bodies, eighths of alpha and eighths of beta of genus K. And what we do is you take a pairwise disjoint collection of embedded curves, sort of alpha 1 through alpha k, abbreviated alpha, such that the alpha i's bound disks at eighths of alpha, and sigma minus the alphas is connected. And then similarly, you define beta to be that thing. And you sort of pick some baseline, which is not particularly important in this case. Now, you consider a particular strange stream manifold, which is 0, 1 cross sigma. And what we're going to do is write down something that looks very similar to the embedded contact homology chain complex. And the chain complex consists of k tuples of wave chords, 0, 1 cross xi, where xi is an intersection point of some alpha I and some beta of sigma I for some permutation sigma. You're basically intersecting alphas and betas, and then you need to pick 1 point from each alpha and 1 point from each beta. And this is somehow the way to do this. And you often write sort of boldface x for k tuples of wave chords to define this. there's a symplectic slash holomorphic fibration of R cross 01 cross sigma over R cross 01. So this is really a little bit unpleasant, but if you've never seen it, it's probably a little bit, it took me a while to sort of understand what's going on. But this is the base. Okay? You have R in this direction, and this is the 0, 1 direction. Okay? And over each point, so you take some sort of point, and over each point you have a fiber which looks like sigma. Is that good? So you have R cross 0, 1 cross sigma over R cross 0, 1, and these first two coordinates are somehow holomorphic, right? And then this one's also, you think of as holomorphic. So somehow the funny thing is that 4 dimensions split up into 2 plus 2 or 1 plus 3. So here we're thinking of it as being split up into 2 plus 2, right? Whereas if you think in terms of the symplectization, it's basically 1 plus 3. Like, do you see my hand's a little wobbly, but does that make sense? We're sort of somehow using the fact that 2 plus 2 equals 1 plus 3. Okay.
What's the math by? Just projection?
Yeah, it's just a straightforward projection onto the first two factors. And you can take everything in sight to be holomorphic. So these two, you have a strip as such. That's just the usual holomorphic strip. And then you have sigma, you just put some complex structure on it, and then you just project to the first two. Right. So this situation is almost the same as the embedded contact homology situation. You want to count differentials. So in this case, you count isolated embedded degree k holomorphic multi-sections of pi, which satisfy the following things. It's asymptotic to 0, 1 cross x at the positive end, and to 0, 1 cross y at the negative end. So, for ECH, it looks like this. In our case, you have some sort of collection, right, of waveboards. You have some collection of waveboards, and you call this x cross 0, 1, so 0, 1 cross x. And then you have another collection of waveboards at negative infinity, which will be called 0, 1 cross y. And then you're interested in homomorphic curves from here to there, which sort of asymptotically approach these things at infinity. And, well, if you just kind of project it this way, what you're going to find is that you're going to have some sort of branch cover of the base. If you sort of project down to the base, you're going to get some sort of branch cover. But sort of upstairs, you're going to have some sort of multi-section, which intersects each fiber exactly k times. And then at positive infinity, you're approaching something, waveboards that look like 0, 1 cross x, and at negative infinity, you're approaching waveboards which look like 0, 1 cross y. Oh, the boundary conditions are following. So boundary of C is a subset of R cross 1 cross alpha. So on the left side, there's a Lagrangian which looks like R cross 1 cross alpha. And on the left side, on the right side, you have a Lagrangian which looks like R cross 0 cross beta. And you need to somehow use each R cross 1 cross alpha I once. You need to, each boundary, so what does it say? So each boundary component needs to map to this or that. And you need to use each component of R cross 0 cross alpha or R cross 0 cross beta exactly once. And lastly, there's some sort of intersection thing. Good? I'm not sure if it's good, but hopefully you get some sort of gestalt, I don't know, picture of what's going on. Okay, so what we'd like to do is now, start with, we have an open book decomposition. So we'd like to write down a Hagar diagram for the ECH side, what we did was rephrase everything in terms of just a page of an open book decomposition, right? And then the monodromy on the page. On the Haggard 4 side, what you'd like to do is basically the same thing. So first of all, what's a compatible Haggard diagram for an open book decomposition? Well, you can take, so roughly the way to think about it, can I use your notebook again, is well, you have your stack of papers, you sort of cut it in half, you sort of take just half of it, and one of them is like S cross 0 to 1 half, and the other half is S cross 1 half to 1. And it turns out that each of these stacks of papers is a Haggard, it's a handlebar. And if you've never seen this before, then it's not so easy to see, but it's a good exercise. And then the boundary of it, of the Haggard, of the sort of Haggard splitting, is a Haggard surface, which is basically S cross 1 half union S cross 0. And so you actually at least have a Haggard surface which has something to do with S's. Now, what you'd like to do is you pick a basis, what I call a basis, a collection of properly embedded arcs on S, such that S minus, so when you cut S along these arcs, you get a polygon. Can I actually draw something with Blackboard? So the picture is actually not, the thing is, this surface S really does not have connected boundaries, but it's probably easier to draw. Okay. So what you'd like to do is take arcs A1, A2. So you pick arcs A1, A2 such that, well, they cut off S into just a disk. So that's the basis. And what you do is you take BI, which is the push off of AI, in the direction of boundary S. So the boundary is this way, and you push it off. This is B1 and this is B2. If you're in Haggard 4 aficionado, you've seen me do this many times, so just switch your brain off. And you somehow push the arc in this way, and you get some sort of standard looking intersections. Like this is X1 and this is X2. Okay, now what you do, you take the alpha I to be boundary of AI cross 0, 1 half. And then BI to be, beta I to be boundary of BI cross 1 half 1. And then if you sort of apply the monodromy, you get BI cross 1 half union H of BI cross 0. So roughly speaking, what's happening is that this is somehow the intersection pattern of the A's and B's on S cross 1 half. This is somehow the boring stuff that's going on. This is the intersection pattern on S cross 1 half. On the other side, maybe I should just draw it over here. On the other side, we have basically the same thing. Right? You have A's, but then the B's are sort of, you apply the monodromy, you apply H to the B's, so you don't really know what it's doing. It sort of does maybe something like this, and then maybe that. So on sort of the top face, there are basically nothing interesting is going on. And the bottom side, sort of all the interesting stuff is going on. And what we'd like to do is just, well, okay, somehow the only thing that's non-trivial is the xi's. So what we do is we just somehow transfer. Okay, so I'm just going to change the intersections so they're here. And pretend we have xi's. These are both xi's. They appear twice in the diagram, but at least you can sort of draw everything. So this is x1, here's x1, maybe this is x2. So at least you can draw sort of all the intersection points on a page of the open book. Is that good? Okay. And the one last remark here is that to be, so if you just take the sort of collection of xi's, okay, if you just take the tuple points here, then that's actually the contact invariant corresponding in Haggard flow homology corresponding to the particular contact structure. So in some senses, it's like the ground state, which basically means, okay, so maybe that's the only thing I'm going to say for the moment. Right, so the xi's, the 2G tuple x1 through x2G gives rise to the contact invariant in Haggard flow homology. Okay, so what we did over there is we placed 2 copies of xi on the boundary of S cross 0. And then in that case, you can just write the Haggard flow homology chain complex chain group as just that. Something just defined, that's defined strictly in terms of S. Okay, so let me say a little bit more about the contact invariant. So on the ECH side, the contact invariant is generated by this empty set. And it's also generated, like, it also has something to do with E that I said before. On the Haggard 4 side, you have Y, you might have some Y's which are on the S cross 0 portion, and you can have some sort of tuples in the contact class. Is that sort of okay for the moment? Then this thing, if you sort of think in terms of how it should correspond to in embedded contact homology, it really needs to correspond to an orbit set which intersects a page exactly k times. Right? So these are basically ground states. Somehow you can sort of just cross them out mentally. And then you're just left with k tuples. And then that should actually correspond to an orbit set which intersects the page k times. That's somehow the principle. So the thing is, you're in Haggard flow homology, you're always taking things which intersect, sort of, let's say, exactly which tuples, which are sort of 2G tuples, sort of exactly on the nose. Whereas in embedded contact homology, you're allowing yourself sort of, an arbitrary number of intersections. And roughly speaking, this is somehow a way to relate. Basically, what we're going to be doing is comparing ECH of things which intersect up to 2G times together with Haggard flow homology. And then afterwards, we have to do some sort of stabilization operation to somehow, you need to do some direct limit operation to somehow keep track of everything else. But at least the first order approximation, you're relating embedded contact homology groups of things which intersect the page up to 2G times, and then Haggard flow homology. Okay, so again, so the setting here is that we're now counting isolated embedded homomorphic degree 2G multi-sections of something that looks like this with fiber S. So on the ECH side now, on the ECH side you have a base which looks like a cylinder and has fiber S. Right? On the Haggard 4 side, you actually have sort of an infinite strip with fiber S. We've actually somehow went from sigma to S. So is that okay? So we actually have things which look very similar. One has fiber, both of them have fiber S. One is a strip, the other is a cylinder. Okay, so there's some sort of machine that you can plug in to sort of go from one to the other. And maybe as an intermediary, let me explain broken closed string. So maybe can I turn on the light? Sorry. Okay, so what's a broken closed string? So suppose you have, this is some portion of S, and then you sort of stack across it with 0, 1, so this. And then you have your alpha arcs. You have arcs like this. This is maybe A1, this is A2. And you apply the monodromy, so maybe you get something that looks like H of A2, and then maybe H of A1. And a broken closed string is some sort of topological type of something. And what you do is, suppose you have an intersection is identified with maybe that piece, right, on the modern domain. So you just sort of follow, you sort of go here, and then do some sort of following. You follow along until you get to x2, which is the next intersection point between this one and that one. So you sort of maybe follow this way, and then you sort of follow a little bit, and then you sort of come out here, and then you get to x1. So this is somehow a mechanism for starting with a bunch of chords, and then somehow doing some sort of closing procedure by attaching arcs in the AIs. So you sort of go up, move, go up, move, and is that sort of okay? So you have the A's and you have the H of A's, and you have chords between them. You can go up and then move along the chords, move along the A's, right? And then moving along here is the same as moving somewhere else downstairs. Okay? And then you move up, and then so on. So this sort of closes up to certain things that will close. That's somehow the broken closed string technology. And well, to do this, to do the broken closed string business, well, vigorously you do the following thing. You try to define a chain map P from sort of, let's say, CF hat to ECC sub 2G, and you count isolated degree 2G homomorphic multi-sections in a certain symplectic vibration pi, well, with a certain base. I'm going to show you the base in a moment, which approach some sort of two-pole y at the positive end and an orbit set at a negative end. And, well, and the chain map is motivated by combining the work of Zeidel and Donaldson-Smith. So the base sort of looks like this. So what is this? So at the positive end, it looks basically like an infinite strip. And then this is boundary. These two things are identified, and you actually have, and this is also, this is not a boundary, this is just sort of pulled off from negative. So another way of drawing this is perhaps you have something that looks like this, and you have something that looks like that. So you're counting homomorphic curves with strips at positive end and cylinders at negative end. And, well, there's some sort of, it's supposed to be a machine which turns chords into closed orbits. Or sort of collections of chords into collections of closed orbits. And the reason you can put it in this machine is that all the fibers, and the fibers are all S. Right? And you can sort of put it in because you've sort of normalized everything so that you're only dealing with things with fiber S. Okay, and then the Lagrangian boundary condition, I probably should just go back to the picture. So maybe you pick any point here that you want, and at this point you put your favorite copy of A, right? So favorite copy of AI, and what you can do is there's this thing called parallel transport. When you have a symplectic vibration, you can sort of parallel transport this way, parallel transport all the way like this, and when you parallel transport, you actually get a Lagrangian on the whole symplectic sort of vibration. So you get a Lagrangian on the boundary, and that gives you the Lagrangian boundary. So that's roughly what it says. Place a copy of AI on one fiber that's sitting above the boundary of B plus. So boundary B, apply parallel transport to AI, and this is sort of standard symplectic machine. Then it sweeps out a Lagrangian, which restricts to a subset of R cross 0, 1, R cross 1 cross AI, and R cross 0 cross H of AI at the positive. Okay, so you have to, okay, so you can, it's not too hard to show that P is a chain map which induces an isomorphism, it's not too hard to show that P is a chain map. The claim is that it actually induces an isomorphism on the level of homology. And how do you actually show that something induces an isomorphism and produce its inverse? Well, based on what we've been discussing, what's a reasonable candidate for the inverse? Well, why don't we just sort of flip the picture and draw something that's upside down? Or sort of, why don't we just draw something that looks like that? Okay. And that should that should be its inverse. So it turns out that it's not. It's actually far from an inverse. It sort of does, this particular thing doesn't quite work. And this is where the talk ends, but the real work starts. So the real work is to figure out exactly what you do. So what you have to do, and why it works is sort of a mystery to us at this moment. What you do is you sort of pick a point. So instead of picking sort of S that looks like this, we actually sort of put in an n, you sort of put in an infinite n that looks like this, and then maybe sort of eventually compactify. And so initially you have S, and then you have some sort of compactification, which we call S bar. And we count holomorphic sort of degree 2G holomorphic multi-sections, which actually sort of go through a particular strange, like sort of particular sort of preferred point at sort of at infinity. And when you do this particular count, it turns out that the indices actually work. And you sort of start becoming optimistic. And if you sort of actually, and it turns out that you actually run into a horde of sort of difficulties. And one of them is that you can have like really, really strange, usually when you sort of take a sequence of holomorphic curves, it breaks into something relatively mild. Usually something like in 2 pieces. But in our particular case, when we actually sort of put in this thing, which we call the volcano, you actually could get things which would sort of with many pieces, and you have to work really hard to eliminate basically all of them. So it turns out that, well, the psi map is actually the hard part of the work. The rest of the stuff is actually pretty straightforward. Defining the psi map and showing it's actually a chain. It gives you B composed of psi is chain homotopic to the identity is also rather not straightforward.